Let's start with a thought experiment. Imagine you place a perfectly fresh apple inside a sealed three-dimensional box. If you check on it just a few weeks later, that apple will be completely shriveled and decayed. For an object to rot, it must change state, and that change requires an axis beyond the physical three. Time provides the stage where biological decay and physical movement play out. Without this fourth dimension, the universe remains a frozen photograph, devoid of the ability for matter to age or evolve. Humanity spent centuries operating under the assumption that reality was strictly three-dimensional. Our understanding was rooted in ancient geometric definitions of flat shapes and straight lines, which viewed the world as a static physical container. In 1905, Albert Einstein, working as a patent clerk, proposed that time is an actual physical dimension that we are constantly moving through. Einstein's discovery implies that time travel is a tangible property of our universe, rather than a literary device. In fact, we have already successfully demonstrated it. Russian cosmonaut Sergei Krikalev is the first verified human time traveler in history. By spending 747 days living on the International Space Station, traveling at high speeds in a low-gravity environment, his personal clock ticked slightly out of sync with those on the ground. When he finally returned to Earth, he had physically traveled 0.02 seconds into his own future. While future travel is a documented reality, we still lack the machines required for a more significant leap. This is because the universe imposes specific rules on the direction of our movement. Einstein's theory of relativity describes time as a flexible, stretchable fabric that behaves differently for every observer. This diagram illustrates how space-time responds to mass and motion. The grid lines physically bend and compress when encountering gravity. Under these conditions, time slows down. An object experiencing higher gravity sees its personal clock tick slower compared to the universe. Time is entirely relative. Your personal rate of aging is determined specifically by your velocity and your proximity to massive gravitational sources. We can observe this phenomenon at the subatomic level with the muon. This cosmic ray is born in our upper atmosphere with a natural lifespan of exactly 2 microseconds, too short to ever reach the ground. Because muons travel at nearly the speed of light, their internal clock slows down. This velocity effectively stretches their 2 microsecond lifespan to 11 microseconds, providing enough time for them to reach the Earth's surface. In 1971, Joseph Hafele and Richard Keating scaled this experiment up to the human level by placing highly precise atomic clocks on commercial airplanes. After flying around the world at high speeds, those airborne clocks had desynchronized from the stationary clocks left on the ground. These experiments transformed time travel from a mathematical curiosity into a measurable physical phenomenon. To achieve a time jump of centuries rather than milliseconds, we would need to find a way to drastically increase the gravitational forces involved. Black holes function as natural forward time machines. Their immense gravity is so intense that it aggressively warps the light and time surrounding them. Orbiting a black hole for just a few hours would slow your personal passage of time so significantly that you would return home to find centuries had passed on Earth. Reaching the future has transitioned from a theoretical impossibility to an immense engineering challenge. The physics is settled. We simply lack the technology to survive the journey. If reaching the future is a matter of survivable engineering, why does the past remain so inaccessible? The primary barrier is the cosmic speed limit. To observe an event from the past, matter would need to travel faster than the speed of light, a feat that requires an infinite amount of energy and breaks our current laws of physics. Physicist Ronald Mallet is exploring a potential loophole, using concentrated, continuous laser rings to twist and bend spacetime into a closed loop. Another theoretical shortcut is the Einstein-Rosen bridge, or wormhole. This is a hypothetical tunnel that connects two separate points in time by punching through the fabric of the universe. These methods prioritize folding the universe over outrunning a beam of light. They represent our best mathematical attempt to bypass the energy limits that prevent backward travel. Even if a wormhole exists, it is likely microscopic and highly unstable. The immense gravitational pressure of the surrounding universe would crush the tunnel shut the moment it formed. Holding a wormhole open requires exotic matter. Unlike normal matter, it possesses negative mass, pushing outward to counteract gravity. The Casimir effect shows similar forces pushing vacuum plates apart in a lab. However, gathering enough to stabilize a tunnel remains a distant theory. Beyond the physical obstacles, we face the logical barrier of the paradox. If you were to travel to the past and prevent your grandparents from meeting, your parents would never exist. Consequently, you would never be born to attempt the journey. Backward time travel is prevented by a combination of impossible energy requirements, hypothetical matter, and self-erasing logical loops. Physics continues to evolve. Recent breakthroughs with gravitational waves and subatomic tarmac balls show that our understanding of the universe is still expanding. For now, we remain time travelers, locked into a forward motion of exactly 1 second per second. Physics allows us to accelerate our journey into the future, but the laws of the universe provide no mechanism to return, leaving our timeline fixed in a forward trajectory.